Hello, and welcome to this presentation, Understanding LCR Meters. This presentation will provide you with a brief technical introduction to LCR meters and the most common measurements made using LCR meters. Let's start by talking about the three most fundamental building blocks in electronics, namely resistors, capacitors, and inductors. Almost all electronic devices use some combination of these three components to control the current and/or voltage at different points in a circuit. The degree to which these components affect the current or voltage is a function of their impedance. Impedance, or the opposition to the flow of current, consists of resistance and/or reactance. An ideal resistance doesn't change with the frequency of the signal. As you might imagine, this is the kind of impedance normally associated with resistors. The other type is reactance, where the opposition to the current or voltage does change as a function of frequency. Reactance can be further divided into inductive or positive reactance and capacitive or negative reactance. These are, unsurprisingly, most often created by inductors and capacitors. Impedance, therefore, is a complex value, which can be described in two ways. One way is as a real part and as an imaginary part. Another way is as a magnitude and a phase angle. Two very simple formulas can be used to convert between these two different representations of complex impedance. Determining the values of inductance, capacitance, and resistance therefore involves two steps. First, we determine the complex impedance, either in Cartesian or in polar form. The next step is to convert the reactive part of this complex impedance into capacitance or inductance, again using some simple formulas. A pure resistance, that is, one with no complex or reactive part, can be measured with a basic digital multimeter using a DC signal. The impedance of a capacitor or inductor, on the other hand, is frequency dependent, and therefore must be measured using an AC signal, often at different frequencies, and sometimes at different levels or voltages as well. The traditional method for measuring a complex impedance is using a so-called LCR bridge. An LCR bridge consists of four impedances, with Z dot being the device under test or unknown impedance. An AC source is connected to the bridge, and the current is measured between these 2 points. The other impedances are chosen and/or changed until the current flowing through the meter is zero, at which point Z dot can be calculated, again using another simple formula. Another way to calculate a complex impedance is using the phase shift between voltage and current. As you should already know, voltage and current are in phase for pure resistances. That is, the maximum voltage and maximum current both occur at the same time. A reactance, on the other hand, causes the voltage and current to be out of phase. In the case of inductance, the voltage leads the current, and in the case of capacitance, the current leads the voltage. In either case, we can use the amount and the direction of phase shift to determine the amount and type of reactance that caused it. Modern LCR meters use a special auto-balancing bridge to determine the magnitude of the voltage and current, as well as the phase shift or angle between them. As mentioned a moment ago, these values are used to calculate the complex impedance of the device under test, that is, the resistive and reactive parts of the impedance. These in turn are converted into L, C, and R, in henries, farads, and ohms as appropriate. It's also possible to use an LCR meter to determine various transformer parameters, something we'll come back to in a few minutes. In addition to L, C, and R, additional quantities, such as the loss angle and quality factor, can also be derived from these fundamental values. So let's spend a few moments discussing both of these. Recall that an ideal resistor would be purely resistive. In this case, the voltage and current would be in phase, so the phase angle, theta, between them would be 0 degrees. An ideal capacitor, or inductor, would be purely reactive, with a phase angle of plus 90 degrees for an ideal inductor, or minus 90 degrees for an ideal capacitor. In real-world devices, the closer the phase angle is to 90 degrees, the more ideally reactive it is. Let's go back to our diagram with real and imaginary axes. The real axis represents resistance. The positive part of the imaginary axis represents inductance, and the negative part represents capacitance. An ideal inductor would have a positive 90-degree phase angle, but real inductors are not purely reactive, and therefore have a phase angle of less than 90 degrees. A phase angle of less than 90 degrees indicates some resistive loss in the component, and therefore the loss angle is defined as the complement of the phase angle. For example, if the phase angle theta were 80 degrees, the loss angle delta would be 90 minus 80, or 10 degrees. The quality factor, or Q, of a reactive component is another way of expressing how ideal a reactance is. Higher values of Q mean a more pure reactance, which is desirable in almost all cases. Q can be calculated in two ways, either as the reactance X over the resistance R, or by taking the tangent of the phase angle theta. Typical values of Q are in the range of tens to low thousands, but as can be seen in the diagram, Q can also vary strongly with frequency. In some cases, particularly when measuring capacitance, the dissipation factor D is used instead of the quality factor Q. D is just the reciprocal of Q, or can be computed by taking the tangent of the loss angle delta. We mentioned earlier that LCR meters can also be used to make various transformer measurements. These include the turns ratio, N, which can be calculated from the ratio of primary voltage to secondary voltage. Another measurement is mutual inductance, which is the change in voltage in one winding, or coil, in response to a change in current in the other coil. The phase angle between the signals in the two coils can also be determined. In addition to measuring the inductance of the primary and secondary coils, LCR meters can also be used to find the leakage inductance, which quantifies the imperfect magnetic coupling between these two coils. We don't have time to go into the details of these parameters here, so please see the separate presentation, Understanding Transformer Testing, if you'd like to learn more about these and other transformer measurements. Now let's look at some of the more important topics when it comes to making measurements with LCR meters. These are connections, circuit mode, measurement frequency, measurement level, and bias. We'll start by looking at connections. Electronic components come in a wide variety of packages or form factors, for example, those with leads, surface mount components, etc., and therefore an LCR meter must be connected to them in different ways. In order to accommodate this wide range of form factors, different types of fixtures are used. For example, one type of fixture is used for components with axial or radial leads. Another common fixture type uses Kelvin clip leads, something we'll come back to in just a moment. And special fixtures are also used when measuring transformers. It's important to remember that impedance measurements are affected by the connection between the meter and the device under test. Therefore, correction routines, usually performed using an open and a short, are used to reduce the effect of stray capacitances, inductances, and resistances in the text fixtures, leads, and terminals. Before we move on, let's stop for a moment to discuss Kelvin or 4-wire measurements. The cables connected to our meter have resistance, and although this resistance is typically very small, it does cause a voltage drop between the meter and the device under test. In many cases, this very small drop can be ignored, but it can become significant when measuring small resistances. Kelvin or 4-wire measurements are used to overcome this issue. In a 4-wire measurement, 2 leads carry the current, but 2 additional leads are used to measure the potential or voltage at the device under test. These leads are connected to a very high impedance, so there's almost no current flow in these leads, and therefore almost no voltage drop. This allows the meter to measure voltage almost directly at the load, with minimal impact from the test leads. In most cases, these 4 leads are packaged as a set of Kelvin clip connectors with 4 wires, but only 2 clip-on style connectors. Complex impedances consist of a resistance and a reactance, and these can be modeled either as a series circuit or as a parallel circuit. When measuring reactance with an LCR meter, one of these equivalent circuit models must be chosen. Generally speaking, the series model is used when measuring inductance, and the parallel model is used when measuring capacitance. However, the appropriate model may also depend on the magnitude of the reactance. For example, when measuring large inductors, the parallel model is often more appropriate. The reasons and criteria for choosing a model are somewhat involved, but most LCR meters will automatically choose the most appropriate model for a given measurement. Next, let's talk about measurement frequency. Recall that reactive components, such as capacitors and inductors, are tested with alternating current because their parameters, such as reactance and Q, are frequency dependent. In most cases, reactive components should be measured at the frequency of intended application, or across the expected application frequency range. Older or traditional LCR meters often only measured at discrete frequency points, but newer meters are able to measure by sweeping across the defined frequency range. And although resistors are normally tested with DC, note that even these pure resistances may contain some reactance when tested using AC at different frequencies. Equally important is the level used in making measurements. Just as in the case of frequency, components should be tested at the voltage and/or current levels normally encountered in the intended application. This is because, in many cases, the reactance of a component may change depending on the level of voltage or current applied to it. It's also important to avoid excessive signal levels, since these can damage or destroy the component under test. Bias is another aspect of measurement level. Biasing superimposes a DC voltage or current on the test signal. This can be used to shift the operating point of some types of components when necessary for accurate measurements. For example, inductors may require a higher current than the test current provided by the meter. And some types of capacitors, such as electrolytic or tantalum, may require a positively biased voltage for accurate measurements. LCR meters therefore typically allow bias to be added in two ways, either using an internal bias source or by means of an external source in cases where higher bias voltages are required. Let's end with a brief summary. Impedance is a complex frequency-dependent value consisting of a resistive or real part and/or a reactive or imaginary part. LCR meters quantify this complex impedance by measuring the magnitude of the voltage and current and the phase angle between them. These impedances can then be easily converted into the basic quantities of inductance, capacitance, and resistance, as well as into other useful parameters, such as the quality factor Q. LCR meters can also be used to perform a variety of transformer tests. In most cases, special fixtures are used to connect to the device under test, and a correction or a calibration routine is used to remove the influence of this fixture from the measurement. And lastly, when making measurements with an LCR meter, there are four basic configuration parameters: circuit model, frequency, level, and bias. This concludes our presentation, Understanding LCR Meters. Thanks for watching.